Transfer functions are a very important way of modeling vibrations and are used generically in control theory to model any number of complex things. So we're going to simply talk about them in terms of transfer functions here, but you'll see them in future classes in terms of modeling control, or you'll see them in grad school or your career as you move forward, right? One of the issues that you've seen is that we've only done sinusoidal inputs up to now, right? And so developing solutions for all the different potential types of inputs you have can be quite challenging, right? So you might have, you might have sinusoidal inputs, directly applied. You might have sinusoidal inputs applied to the base. You might have an impulse. Or you might have an arbitrary. You could even have a random input. We'll talk about that more, but that just means you understand the statistics of the input, but you don't actually know in any specific point in time what the input is, right? So what might the issue with this be? Or how do we model this? So we want a simplified form to model this, right? And so we are going to put everything into a generic system H. Let's just say we have a system. And we're going to call it H. In control theory, this is often called a plant, right? Like a manufacturing plant where you bring in materials out of like talking about batteries this morning. So you bring in, all sorts of chemicals and cylinders and metal into your plant, and then out you get batteries. You might actually think of an actual plant. You bring in sunlight and nutrients from the soil, and then you get out fiber for your, your clothes, or whatever else you need fiber for. So we have a plant, and then input. The plant's going to have some input, and we're going to use the term F, which is a little bit different than how we typically write it in control theory, but that's just because we're talking about vibrations, and our only input's F. So makes sense. Keep it simple. Keep it moving along with what we're doing in this class. And we have some sort of output. And X. And that is our transfer function approach, and is commonly used as the formulation and solution of dynamic problems in control literature, right? And can be used for kind of solving various forced function approaches, right? So we need a way to solve this, and to solve this, we want to use Laplace. Which is more broadly kind of integral transforms. And we have been working in the T space. We've been working in the time domain. Every solution so far we have asked for has been in the time domain. And we want to move our solution into the S space, which is just a function of space, right? So by transforming the whole differential equation from the time domain into our lower order function space, the problem becomes easier to solve as the function can be directly manipulated algebraically, right? So this just makes it easier. I'm going to maybe make that in blue. So makes solving easier. Okay, so interesting. Fun fact time. This is Laplace. And why I like Laplace is in Laplace, at the military academy taught Napoleon, during the artillery classes, right? So Napoleon was an artillery commander, and the only people who used to kind of go to school from military commands were artillery commanders. Everyone else was kind of royal, but you wanted people who were good with math if you're doing artillery. And then when Napoleon came to power, he conveniently switched sides to Napoleon's side. And got to keep his comfy job. Became a count of the empire in 1806, and a marquis in kind of 1817. And then after the restoration of the monarchy, he switched sides again. So that's what I like about Laplace. He's a survivor. So if you're wondering why he's my favorite, that's one of the reasons. So it's pretty impressive. Right? There was a violent time in French history, and he made it through the entire time and kept his job. So pretty good. We could all learn something from Laplace. Okay, so he did a lot of things. Of interest to this class is the Laplace transform. We're going to write it like this. For the function f of t, and so often we can write that as a Laplace function of f of t is used as a method for solving the differential equation of motion by reducing the computation needed to that of integration and algebraic manipulation, right? So the definition of the Laplace of f of t looks like this. My Laplace function of f of t is equal to capital F of s. That is my input to my plant in my S domain. So I'm now out of the time domain. I use Laplace to transfer, to take a trip from my time domain to my S domain. And that is equal to the integral, if I knew how to, from 0 to infinity, of f of t e to the negative st dt. Another thing to consider here is that f of t is equal to 0 for t less than 0. So this is only considering for the time domain moving forward, right? We're not looking back. So we in this class, right, we deal with displacement. So f of t gives us displacement, but we also want to deal with our velocity terms, right? So we need to integrate this. So we are going to take the Laplace, let me move it to the left. The Laplace of f of t is equal to our integral from 0 to infinity of f dot of t e to the negative st dt. So I need to take that derivative, so I can just break that out into my integral from 0 to infinity of e to the negative st d of ft with respect to dt, and then again with respect to dt. So integration by parts results in a Laplace of f dot of t is equal to e to the negative st solved between 0 and infinity plus the S domain integral from 0 to infinity of e to the negative st f of t d of t. All right, so this term here, 0 to the e negative STF ft dt is just this input here. So that's my, we'll make that an arrow. It's just going to equal f of s. So a little bit of rearranging, and I get this equation. So if you don't write much down, write this one down. The Laplace of f of t is equal to f of s minus f naught. All right, so that's my kind of velocity term in the Laplace space, right? So I need to get my acceleration relevant term. And so that's going to be the Laplace of f double dot of t. You just have to solve twice, but that just ends up as s squared f of s. So that's my s variable squared times my forcing function in the s domain, minus s times f, well, that's kind of confusing, minus s times f naught, and that's what will end up being my initial conditions, minus f dot naught, so my more initial conditions. Okay, so a few key points on the Laplace transform, right? So the domain of the problem changes from the real number line t to the s domain. The integration of a Laplace transform changes differentiation into multiplication. The transform process is linear, right? So therefore, the transform of a combination of two transforms is the same as a linear transform of these functions. So you will have on the back of your notes, you can download it from Blackboard, and also at the very end of the chapter, it's a whole list of Laplace transforms. You can find these in calculus books, but these are rewritten in the variables that we use in this class, just so there's no confusion, right? Just so there's less confusion, right? But they use the variables omega instead of a, b, c, and you're trying to put things together, right? Okay, so to move from the integration to the time domain to the complex, we use tables and these pre-solved integrals. We're not typically solving the Laplace transforms. I mean, we're just going to use tables. The function x of t can be obtained by taking the inverse Laplace function, right? So x of t, let's say I'm in the Laplace domain, and now I want my displacement, right? Because I'm starting with f, that's why I've got f in all those equations. But now I want x of t. I want to know how my system moves. So that's just equal to the Laplace of capital X, s. That's my solution. That's my output in my s domain, inverse. And that's how I get my output in my s domain, right? So another way to write that is we can solve all those out, but we don't have to. So the output, so the system inputs I just gave you, well, let's rewrite them, right? A little bit redundant, but we'll go inputs, because green is a cool color for inputs. So the Laplace of f of t is equal to f of s. The Laplace of f dot of t is equal to s f of s minus f naught. And then the Laplace of f double dot of t is equal to s squared f of s minus s f of 0 minus f naught of 0. All right, and then let's do orange. Our outputs is equal to our Laplace of x of t. I see now that this one is wrong. F of t, like that. Our Laplace x of t, that's a capital X, sorry, that's a lowercase x, is equal to capital X of s. And then our Laplace of x dot of t is equal to s x of s minus x of 0 and our Laplace x double dot of t is equal to s squared x of s minus s of lowercase x. I'm going to make this one bigger. So this is a capital X. So the lowercase x of 0 minus x dot of 0. Just like before, but now with x's.